Welcome to the second mini lecture this week on second order systems, and in this lecture we're looking at an example of a jacketed reactor to see what happens when you have a cascade of non-interacting processes. So the lecture notes illustrate this example. Here we have a reactor vessel which has temperature T and it's surrounded by a jacket of cooling water in this case, and the cooling water comes in at temperature TW and then reaches a temperature T jacket in the jacket. And we want to know, well, how does the temperature of the reactor change to the temperature TW of the feed water to the jacket? We can break this system down into component parts where we have the jacket and then we have the reactor. So the jacket is a system where the temperature of the feed water into the jacket affects the temperature of the jacket, and that would be a first order process. Likewise, we then have the reactor, and the temperature in the reactor T is affected by the temperature of the jacket, and that's also a first order process. And in this case we're saying that there's no backwards interaction. The temperature of the reactor isn't affecting the temperature of the jacket. There's no process there. So the flow of liquid into the jacket and the volume of the jacket is sufficient to keep that stable and only dependent on the feed water temperature. And so we call that a non-interacting system. How can we model that with our process? Well, let's take a look at it. We have our first process, which relates the temperature of the jacket to the temperature of the water feeding into that jacket, and that would be a first order process, so we can describe it like that. We don't know the details of what the parameters tau and kp are, but we just know that it will behave in that manner. And likewise, the reactor temperature will be dependent on the jacket temperature. Again, it's a first order process. We don't know the details of how it will behave, but we know it will be of this form with a suitable value of kp2 and tau2. So if we want to see how that combines, well, here's T jacket, and we can simply substitute in our expression for T jacket into it. So that's the first part, and then substituting in T jacket here multiplies together the two first order transfer functions, and this will give us obviously a combined transfer function which is second order. And that's how non-interacting systems work. By non-interacting we mean that there's forward behaviour. The temperature of the jacket is affected by the temperature of the feed water affects the temperature of the jacket of the jacket affects the temperature of the reactor, but there's no significant backwards interaction. So the non-interacting systems are simple to model. We simply multiply together the individual transfer functions. So we can see that in the notes here. That's what we've got here. We've multiplied together the two individual transfer functions to get the second order system, and that's where they can come from. So some comments. Chemical processes often involve this type of process. We have two or more processes in sequence. When they mutually interact, we call that an interacting system, and we'll look at that in the next mini lecture. And now we're looking at the one-way interaction, and that's what we call a non-interacting system. And can you see the difference here in this two sketch? This is two tanks which are being fed one to the other. Which is interacting and which is non-interacting? Okay, well, look at this case here. Water flows into this tank and then flows out of the tank into this tank. Two levels, there's a height here and a height here. But it doesn't matter what the height is in this second tank. That's not going to affect what's happening in the first tank. The water will flow out of the first tank into the second tank regardless of what the height of the second tank is. But in this case you can see it's different. Here the water's flowing into tank 1 and this has a height h1, this has a height h2, and now the flow of water from tank 1 to tank 2 is going to be affected by the height of water in tank 2. So here we have a non-interacting system and here we have an interacting system. For the non-interacting system, each of these is again described by a first order process, and together they combine as the product and that creates a second order process. So what can we learn about their behaviour by considering this transfer function? Well, we can see the transfer function looks like this. It's the combined version, and we know that we can deduce something about its behaviour by looking at the poles of the transfer function. Remember, the poles are the roots of the denominator. So the poles will occur when this term is 0 and when this term is 0, and so that means that s is equal to minus tau 1 reciprocated, or here minus tau 2 reciprocated. That gives one pole, that gives the other pole. And what do we know about these? Well, tau is a real, positive real number, and so we're going to end up with two real and distinct poles. We saw before that real and distinct poles correspond to overdamped systems. If the pole is equal to 1, then it's critically damped. If the poles are greater than 1, then it's overdamped. And if the poles are less than 1, then it's underdamped. So if the poles are complex, then it's underdamped. And so these can never be complex, so it must either be critically damped or overdamped. And this carries on as you add more and more processes in your sequence, as long as they're non-interacting. We have 1, 2, carry on till n, will simply just be the combined product of all the transfer functions of the individual ones. I guess that becomes more complicated as it goes on, but the basic behaviour is pretty simple. If you consider two of them and consider what happens if one of them is extremely fast. So if tau 1, for example, if this is really quick, the process time tends to 0. Well, as that tends to 0, then it's just this transfer function which dominates the behaviour. So even if one of your processes is fast, the overall combined process is at best going to be as slow as the slowest sub-process. And in general, as you add these up, it's going to get slower still. So a non-interacting process is going to be as slow as or slower than the slowest element within it. And so they generally combine to give the dynamics of an overdamped response. Okay, and next mini lecture we will look at the case of interacting systems and see how those behave. Thank you.